This is a presentation for the paper Fine-Grained Complexity of Temporal Problems by Konrad, Dabrowski, Peter Jonsson, Sebastian Ordyniak and George Osipov. So let's define the temporal problems first, and for this we need to recall the definition of the CSP, or the constraint satisfaction problem. So let A be a constraint language, so a set of relations over some domain, and then CSP of A is the following problem. As an instance, we are given a set of variables v and a set of constraints c, and each constraint is of form R v1 through vt, where R is a constraint from the language A, t is arity of R, and v1 through vt are the variables from the set V. The basic question is whether there exists an assignment f that maps every variable to an element of the domain and satisfies every constraint in C. So here is an example of a CSP for temporal reasoning called the point algebra. The domain here is the set of real values, and the relations are binary, less than, equal, and greater than. So here you can see an instance of this problem, and to the right is a satisfying assignment, setting v1 to 0, v2, v4 to 2, and v3 to 1. So it's easy to convince yourself that all the constraints are satisfied to the right by the assignment. Right, so here's another example, the simple temporal problem. Here the relations are v1 minus v2 is within an interval I, and this interval I might be any interval whose endpoints are either integers or plus minus infinity. So here is an instance, and we should remark that the intervals might be closed, open, half open, or even contain a single point, like right here in this constraint. This interval has just one point 0. And this instance is also satisfiable. So to compare simple temporal problem and point algebra, the simple temporal problem is more general. So any relation that we could express in point algebra can be expressed here. For example, the equality is expressed by this interval, and the greater than relation is expressed by this interval. So, but sometimes we need even more expressibility, and then we can add expressibility to a constraint language by allowing disjunctions of its relations. So disjunctive temporal problem, or DTP, is a CSP over a language d omega, which contains every relation of arbitrary arity that can be constructed by taking a disjunction of a finite number of STP relations. And at a binary fragment of this language, we denote it by d2, contains only binary relations from this d omega. Right. So now we have much more expressibility than before, but we have to pay with computational complexity for this. So the STP and point algebra are solvable in polynomial time, and these two problems are NP hard. So maybe we want something in between STP and DTP, so something that's both expressive and not so hard to solve as DTP. Then we can consider a smaller constraint language, and one way of doing this is to allow less intervals in our relations. So now the intervals can have endpoints as an endpoint any integer or plus minus infinity. So let's put a restraint on this and let the intervals only take absolute values up to k for some constant k. Then we get a constraint language d omega. The same can be done for the binary language, and as a result we get for each k a constraint language, and the larger k we allow, the more expressive the language is. So there is this natural containment relation between these languages. So let's look at some of the languages that we arrive at using this construction. So d omega 0 and d2 0 are disjunctive extensions of point algebra. d2 is Allen's interval algebra with unit intervals, and both of these were extensively studied in the literature. So now let's look at the complexity of these problems. So recall, STP is tractable, DTP and binary DTP are NP hard. So what happens for d omega? So CSP over d omega is NP hard for all k. So we didn't gain anything by restricting the intervals. And CSP d2k is polynomial only for k equals 0 and NP hard otherwise. So if you look at this picture, the complexity analysis is not very satisfying, because we cannot, for example, compare the complexity of languages d2.1, d2.2, and d2.3 to each other. They are all deemed NP hard, and there is no way to look at their relative complexity. So if we want to do that, we need to use some more tools than classical complexity, and fine-grained complexity provides us with those tools. So in classical complexity, you look at a problem B, and if you want to prove a lower bound on it, you are looking for a polynomial reduction from 3 satisfiability to B, so it can be any other NP-complete problem here. And then if we find such a reduction, the hypothesis P not equal to NP implies that we cannot solve B in polynomial time. So this gives us a superpolynomial lower bound. So if we want stronger lower bounds, then we need stronger assumptions than P not equal to NP. And the assumption that we use in this paper is a standard assumption, the exponential time hypothesis, which claims that no algorithm can solve 3-set in sub-exponential time. So here, if we can find a size-preserving reduction from 3 satisfiability to the problem B, we can claim that B is not solvable in sub-exponential time, unless the ETH fails. And by size-preserving, we mean that the size of the resulting instance is linear in the number of variables of the 3-set instance that we started with. Now we are ready to present our results. And so suppose that we are given an instance of DTP, and n is the number of variables in it, k is the largest integer in the instance. Then for d omega k, we have an algorithm that runs in 2 to the power of big O n k log n plus log k time, and the lower bound saying that no algorithm can solve this problem in 2 to the little o of n log n unless the ETH fails. So this upper bound and lower bound are essentially tight if we fix k. So the same algorithm works for d omega k, and the same lower bound is tight here as well. For the binary case, we have an improved algorithm that runs in big O of n log n plus log k time, and the matching lower bound. And so probably the most interesting case is this one, the binary DTP language with intervals whose endpoints are bound by k. In this case, we have an algorithm that runs in 2 to the big O of n log log n time, and the lower bound that we have is not tight, so it says that there is no universal constant c, such that CSP over d2k for every k can be solved in the OC to the n time. So why is this not tight? Because there might be a sequence of increasing numbers, c1, c2, and so forth, such that CSP d2k is solvable in ck to the n time. So there still might be single exponential time algorithms for each specific k, but we know that this this sequence will be increasing. So I won't be able to go over all selected proofs, but let's look at one of them. So we prove that CSP over d2k is solvable in 2 to the O n log n time for any fixed k. We show the proof for d21. So here we have binary relations, and the integers we can use are at most 1, so 0 or 1 or minus 1. First we prove that if an instance of this problem is satisfiable, then it has an assignment, a satisfying assignment f that maps all the variables into the interval from 0 up to n plus 1. So this hinges on 2 observations. The first is that we can add or subtract the same constant to every value assigned by a function that satisfies this instance, and still get a satisfying assignment. So then we can move it to 0. And the other observation is that we are working with d21, and for 2 neighboring points we can only constrain them to be at distance more than 1, but we can't demand anything more. So if we set them to distance 1 plus epsilon for any positive epsilon, the constraint will be satisfied. And if you imagine if we space out all these points, all these endpoints, then they should fit into this interval. Right. So why do we need this? Then we can look at this interval from 0 up to n plus 1, and we can divide it into buckets of width 1, and look at which variables fall into which bucket. Consider 2 variables, such that there is at least one bucket in between them. Then we know that the only relation that can hold for these 2 points is this relation, v minus u is within from 1 to infinity. And why is this good? Because the bucket here in between gives us a separation of this instance into 3 parts, such that if we fix the assignments to the variables that fall into this bucket, then the left and the right become independent of each other. We know exactly which constraint might hold for any of them. And then we can solve them recursively. So we can do the divide and conquer here, enumerate all assignments to the variables in this bucket, and then solve the left and the right recursively. So in order for this to work, we need to enumerate all solutions to the variables here, and then we don't want too many variables in this bucket. And in this case, not too many means less than or equal to n divided by log n. Also, we need to ensure that it makes sense to recurse, so there are enough variables on the left and the right. And we could take n divided by any constant, and in this case we took n divided by 3 because it works. So at least n divided by 3 variables here and here, and at most n divided by log n variables here. Then we can solve this instance using recursion. So we call such buckets that have not too many variables sparse. So suppose we have, if we have such a bucket, then we can solve recursively. If we don't have such a bucket, this means that we have many dense buckets in the middle, so buckets that contain more than n divided by log n variables. But we cannot have too many of those buckets, namely we can't have more than log n of those. So we know that if we have a sequence of dense buckets, then their total number is less or equal to log n. And this gives us another separation of the problem. So if I enumerate all solutions to this middle dense part, then the left and the right are also independent and we can solve them recursively. And so this algorithm, so the dominating term in the running time of this algorithm is the one, is the time it takes to enumerate all solutions to this part. And this takes all log n to the power of n time, which is precisely 2 to the power of big O of n log n. And this is the running time of our algorithm. Alright, so now to conclude, I would like to talk a little bit about the connection of this problem to qualitative temporal reasoning. So Allen's interval algebra is a prominent formalism for this. Here we have intervals, and the relations between them can be, so one interval precedes the other one, they meet, they overlap, one is during the other one interval starts the other one interval ends the other one, finishes, and they are equal. So the first 6 of this also admit converses. And as before, we allow disjunctions of these basic relations, and this forms the Allen's interval algebra. So if we consider Allen's interval algebra, but only for the intervals whose length is 1, then we get another constraint language, and it has only 7 relations here. So we lose the relations during starts and finishes, because for unit intervals they cannot be satisfied. So only the 7 basic relations and disjunctions of those. And we show that unit interval algebra is equivalent to the problem CSP D21. And this can be easily seen by just considering the relations. So if I want to, for example, force interval I to meet interval j, then I can say that the left-hand point of j minus the left-hand point of I is equal to 1. And this can be done for every relation in this language. So we can express any interval Allen relation, unit interval Allen relation in the CSPD21 language. And as a consequence of our theorem, we prove that unit interval algebra can be solved in 2 to the O n log n time. So one question that we raise is whether unit interval algebra can be solved in single exponential time. Or maybe we can prove a stronger lower bound that will show that this is the best possible. Another question is whether Allen's interval algebra can be solved either in this time or maybe even in single exponential time. So this would be very interesting to solve. And that's all for now, and thank you for your attention.